Okay. So now what happens? On the last one, it's kind of a funky question. I've never seen this question asked any other way. It's actually genius the way they asked it because you can actually get an answer. But usually on these situations, you could not get an answer.
Isn't it asking for an equation?
Did it ask for equation? On C D?
No, that's what
It says, what would be the final distribution of charge if the spheres were joined by connecting wire? Now, so where are the charges? Question.
well, like if there's a connecting wire.
So I connect a wire. What's going to happen?
The charge like
Would you just do plus?
Electrons are going to rip in down into here. And then I'm going to end up in this place where I have plus Q on the bottom, and I have Q on the outside, right? That's kind of weird. I have nothing on the outside, right?
Right.
So electrons are going to keep swarming in. Now, what?
Like if you're gonna do it, can you do like a cylinder with wire?
I don't know what you're doing. All I'm trying to figure out where the charges are going. This is a conductor, right?
Yeah.
The electrons are going to far apart as they can. Are they going to hang out here, or are they going to hang out here? Right, so all of them are going to go to the outside. My net charge between the two is just 1Q. So the outside would get a plus Q, and the inside would die.
Okay.
This would become uncharged, which is funky, because usually you end up sharing the charge, right? But because one's inside the other side, other one, the farthest apart they can get physically is as far apart as they can, right? So this is not like the ones where you have two that are identical and you tap them, which would be a logical way to look at this problem. Instead, they're saying one on the outside, one on the inside. Well, everything can go to the outside. They can't. They're fleeing.
So when you have plus 2Q and negative 2, why would it balance out to plus 2 plus 2?
And just 1 plus Q. This goes away. The total charge is plus Q. The real question is, does half on here and half on here? Or does it stay on here? Or does it go to the outside? And the answer question, it's not stable until the electrons are far, protons in this case, sort of. The protons are as far apart as they possibly be. Which is on the outside, distributed evenly on the outside. The inside doesn't matter. They're all going to leave the inside until the truth is, what's really happening is electrons are going to go into the center until all the electrons are left the outside shell. That's reality. Since we learned most of our electromagnetism before we even did that. Part of magnetism quarter. All right, I got to pass out 1208. Question of the week. Positive charge certainly would. And I'm going to double check to make sure we're talking about it. It just says electric fields. Electric field way positive charge would go. So now I'm going to go ahead and go, all right, well, at L, is it L is the first one? Yeah. So L is going to go perpendicular to the equal potential lines, and it's going to go downhill. So we go that way, right?
What is that?
Well, here's the surface. It's perpendicular. This is 50 volts. This is 40 volts. So it's going to go downhill.
Oh,
right?
I thought you were talking about the other side.
I haven't gotten anywhere near there. Okay, the next point is N. Let's find N. N's right here. Perpendicular first two, roughly going that way. Next one is U. U is right here. That's U. There's negative 10, so a positive charge would go that way. And they had great flexibility on the direction of these arrows. When I read, if I remember the key correctly. B. And which of the lettered unit points is the electric field the greatest in magnitude? Try that problem out. Think really hard.
What equation?
It's a good question. What equation would you use? What equation relates voltage to electric field? The correct answer is T. Why would it be T? Okay, so the electric field, 10. So we know that the integral of the electric field, am I doing this right? Yeah, integral electric field is equal to voltage, correct? So therefore, the change in voltage with respect to distance is equal to my electric field. Agreed? So the faster my voltage is changing with respect to distance, the steeper my hillside is, the steeper I'm falling down, the greater my electric field. So if we look, the lines here are pretty far apart. It's not falling very fast. But over here, it's falling very fast. Okay? The amount of voltage per little bitty distance is going up. Agreed? I'm looking back at Mr. Reith, who I thought had the wrong answer. We're good?
Yeah.
All right.
think I'm having like a tough time visualizing.
Okay, so remember voltage to equal potential lines. These are equal height in terms of charge rather than in terms of real height. Okay, but it's similar to hills. There's a hill over here. It's sloping down, sloping down, sloping down until this is sea level. And it's still sloping down, sloping down, sloping down until it's below sea level. Okay? So the directions of force would be perpendicular to these lines. Because things would want to roll downhill.
Okay.
Ever seen a contour map? No, that's great. We used to all look at contour maps back in the good old days. They tell you how, so this is a high hill. This is the bottom valley, right? So a positive charge would want to roll down the hill like this.
Okay.
Agreed?
Yeah.
Okay. So it wants to roll down the hill like this. Then this is steep because the fall off's greater here. Whereas this is less steep. And object sitting here is rolling. Here's the hill, right? So it's rolling this way off the hill. This way would roll this way off the hill. This one would roll that way off the hill. And if I was going to draw field lines, which I really shouldn't do, but I'm going to do it anyways because why not? If I was to draw field lines, they would look something like, whoops, it didn't start my pen until way late. All right? Perpendicular to each of those lines.
So the field lines are like where the positive charge is.
They go from the positive to the negative. Don't we draw them from the positive to the negative? Yeah. There's a positive to the negative. A charge would want to go downhill. Equal potential lines are like every place where you equal size on that hill. Right? In the same spot in the electric field. Equivalent. Okay? All right. All right. Compute the magnitude of, go ahead and try C. Compute the magnitude for C.
Do we need a ruler?
Do you need a ruler? You're not allowed to have. So my change in voltage with respect to distance, right? So if I want to find my electric field here, I need to know how fast my electric field is falling along this line, right? So how far is it, first of all? I'd go like this.
So you measure it from like, how far it is from the roller.
Well, I know this is 30 volts. I know this is 20 volts, don't I? So so I just need to know how far it is between those two to find my DR part. Now, it's not linear, so we're approximating. We also don't have a ruler, so we're approximating. So we're going to find that it falls down at 10 volts, which, by the way, would probably make positive, but it doesn't. I don't think it. Nope, it would matter. So we're going to be positive. So positive 10 volts divided by
15 centimeters.
15. This is just 1 centimeter, right?
Yeah.
Maybe like 2 centimeters, doesn't it? 2 centimeters. So 0.02. What I got. So 500 volts per meter, or 500 newtons per coulomb.
If it's 10 to the negative 2, isn't it?
That means centimeters.
But is 1.1 meter 10 centimeters?
That's not 0.1, it's 0.01. Negative 2 is 2 decimal places. It's this.
Why not? Okay.
Right? Because you have to move it 2 places. Get behind it.
Yeah, I thought it was like you started to do that. I thought it was okay.
All right, compute the approximate value for the potential difference between the points M and S. Approximate the voltage difference between M and S. Voltage at M is 40. Voltage at M is 40, right? What's my voltage at S? 5. So what would be the difference between 40 minus 5? 35 volts. That's it. That's as hard as that problem is. Don't make it any harder. Next question, try E. It says, determine the work done on the field moving a 5 times 10 to the negative 12 coulomb charge from M to R. From M to R, how much work is that? Moving in a positive charge of 5 times 10 to the 12 coulombs, or negative 12 coulombs, that distance. Same voltage.
Oh,
Just like we did in the lab, right? You combined all the spots into the same voltage. That's why we did the lab. The only reason the lab is because this problem could be on your test. It's unlikely, but it could be. And this is easy stuff. Like if you get this, it's like, please give me 5 of these. Come on now.
This is actually really easy. I had a
Yes.
really bad.
Okay, so E, it says determine the work done by moving a 5 times 10 to the 12 coulomb from M to R. M is here. Whoops, M is not there because I can't circle it apparently. There's M, there's R. It means I'm dropping a total of 10 volts. 10 volts times, what's the charge I'm dragging? 5 times 10 to the negative 12th. Put a little mathage to it. I get 5.0 times 10 to the negative 11th, right? Joules?
do we want it to be negative?
I'm going to say the work done by the field is positive. The field is pushing it. It says the work done by the field. So the field rolls it down that hill, it's going to do that much work. But that is a great question. But it says work done by the field. How much work would you have to do to get it there would be a negative answer. Because you're rolling it downhill. Okay? All right, F. If the charge were then moved from M to point S and then to point R, would the answer be different? If so, how? Wait, what? Oh, if you move it to S and then R, how would it be different? Is this voltage, total voltage changed? So total voltage is not changed, so therefore the work would be the same. It would be identical. The path does not matter. Perfect. Path does not matter. I like it. Got it? Now this is a good one. I honestly, every so often, so what I've told you before is I can tell you what the 3 problems on the AP test are. What are the 3 problems on the AP test? The first problem is, you're most likely it's going to happen when you look at problem number 1 is you're going to see a sphere. You're like, oh, it's a Gauss. There's a large chance, or largely less chance, that you might see something like this. A disc, or a little piece of wire, or a stick with a point drawn out here. That's the second most likely thing to see in there. The third most likely thing to see is that for problem number 1. Problem number 2, when you pop it open, is going to look a lot like this.
Circuit.
So that's what problem number 2 is likely to look like. Problem number 3 is likely to look like, what's the classic example? That's correct, actually, just I.
I don't know.
I've got a wire with current in it and a square wire above it.
Okay.
And this is your magnetism problem.
I saw something where they had 2 wires and matching one of them was striking the other.
Yes, that's how it